1.2 of the nodes, which are number systems. So in this lecture, we will show how you go from the natural numbers, which are the numbers we use for counting, to the integer numbers, to the rational numbers, to the reals. Okay? So I'm just going to give an overview of all of them. In the notes you have more details if you want to read about them. So and you want to get geeky. Section 1.2 in the note will deal a lot of details to it. But in this lecture it's just a couple of details, and the important point that I will deal with in this lecture is the induction principle. So pay attention to that when I get to it. Okay? So the natural numbers are the numbers that we use for counting. Okay, so 1, 2, 3, 4, 5, and so on. Okay, and this is again curly brackets means that this is a set. We denote them with this letter N, capital N. And so you know all the properties of the natural numbers. You can multiply them, you can sum them, and the problem is that there's no solution for subtraction always. Okay, you can subtract 5 minus 3 and the solution is 2, but 3 minus 5 is nothing. There is no natural number that is a solution of this equation, right? You could say, well, minus 2, but minus 2 is not a natural number. Okay, if you think about the numbers that we use for counting, if you think I have 3 apples and then someone takes 5 apples from me, well, you don't have a solution for that. Okay, so that's in fact why we have to kind of create the integer numbers. Okay, the integer numbers are just the natural numbers plus the negative numbers. Okay, so if the integers are usually written like this with this set, and so they start with minus 3, minus 2, minus 1, 0, and then 1, 2, 3. So you can think of them as having been the naturals union. So this is a union, set union with the set 0, and then union with a copy of the naturals but in negative, so negative naturals. Okay. This is a kind of a way to think about them. Okay, and they're built so that this equation has a solution. Okay, so now you can subtract 3 minus 100, and then this will have a solution. Okay, this is an integer number. Okay, so with integer numbers you can sum, you can subtract, you can multiply them, and you can divide, but then again you don't always have a solution for it. So you have 6 over 3 is 2, or minus 6 over 2 is minus 3, you know that. But was 6 over 4 is, what is this? Well, the solution of this is not an integer number, and so that's why you have to create the rational numbers. Okay, now the rational numbers with this Q, the bar, are every number of this that can be written like this: m over n, when m and n are members of the naturals. Okay, well, not the naturals, actually, the integers. Okay, and we write it like this. Sorry about this. So the way we read this is that the rationals are the set, okay, the curly brackets, that contain every number that has this form, m over n, such that this m and this n are integer numbers. Okay, so 3 over 2, 1 over 4, and so on and so forth. All of them are just rational numbers. Okay, Now, interestingly, the rational numbers can be written in many different ways, because we know that 3 over 2 is the same as 6 over 4, which is the same as 9 over 6, and so on. Okay? And so there are many ways in which you can write one rational number. So now you can sum the rational numbers, you can multiply them, you can subtract them, you can divide them, and you will see, and if you go back to the previous lecture, now the rational numbers are an ordered field. They fulfill all the properties of the ordered fields, so you can do everything with them as we did before with the reals. Okay? But there's a property. Well, there's a thing with not a property, but the thing with the rational numbers is that they are not, and we in math we say they are not complete. Not complete. And what we mean by that is that there are numbers that are how to say it, very close to other rational numbers, but they are not rational. Okay, so if you think about, I told you before about the number line. Okay, this is 0. Okay, well, the rational numbers have a very interesting property, is that very close, if you have any number, m sub 1 over n sub 1, and then this is m sub 2 over n sub 2. Between any two rational numbers, there's always another rational number. Okay, this property is that it means that they are dense. Okay, so well, you can look it up in the notes. Okay, I'm not going to go into detail with this. They are dense. That means that very close to any rational number, there's another rational number. But we can find numbers between the rationals that are not rational numbers. So for instance, and this is the classical example, square root of 2. Okay, square root of 2 is not a rational number. Okay, how do we prove this? Okay, because I can tell you that, but this is math. In math, I have to show you. Okay, so this is a theorem. Okay, I told you that some propositions, when they are important, they are called theorems. This is a theorem, and the theorem says square root is not a rational number. Okay, and I'm going to show the proof because it's a favorite of mine, and it's very easy to see, and I hope you enjoy it. So the way we prove it is we prove it by contradiction. Okay, or so proof by contradiction. Okay, and so we assume the contradiction, which is square root of 2 is a rational number. Okay, assume this is true. Okay, p and q are integers. Okay, and we assume furthermore that they have no common factors. No common factors. And this is easy to assume because suppose p is 2 times 6 times a number m, and then q is 2 times 6 times a number n, then we could write p over q as 2 plus 6 times m, 2 times 6 times n, and these things cancel each other out, and this is the same as n over n, and m over n do not have common factors. Okay, and if they had, we could keep going like this up until they had no common factors. Okay, so p and q have no common factors. Okay, so now let's square both sides. So this is 2, and this is p squared over q squared. Now we can multiply both sides by q squared. 2 times q squared is equal to p squared. Now this implies that p squared is even. Okay, right? Because it's 2 times a number. But now this implies that p is even, because the square of an odd number is an odd number. Okay, you multiply 2 times an odd number, you will have an odd number. So p is even. So that means we can write p as 2 times k, for instance. Okay, so if we subtract here, we have 2q squared is 4 times k squared. which implies that q squared is 2 times k squared. But using the same argument as here, this means that q is even. But wait a minute, p is even, q is even, so that means they have one common factor at least, which is 2. But we said that p and q didn't have a common factor, so that means we have reached a contradiction. Okay, we started with some assumptions. Okay, square root of 2 is rational, and these two guys do not have common factors. Now we reach a contradiction. If we assume this, now these two guys have a common factor, which means this thing cannot be true. Okay, so then we cannot write square root of 2 as a rational number. Square root of 2 does not belong to the rationals. Okay, so that's the proof. Now, interestingly, back in the day, many centuries ago, the Greeks, led by Pythagoras, which I guess you know him because of the triangles, they had kind of a beautiful theory about numbers and how, you know, different fractions and, you know, ratios and things like that were behind the rules of the universe, and everything was beautiful because of the rational numbers and things like that, and they believed that everything could be explained because of the rational numbers. Well, the legend says that there was a guy, there was a follower of Pythagoras that proved this thing. They said, wait a minute, I found a number, which is square root of 2, that is not a rational number. So what happens with that? Okay, up until then, everybody thought that every number could be expressed as a fraction of 2 other numbers. But this guy said, well, actually not. You know, I found a number, square root of 2, that's not a rational number. And so the legend says that Pythagoras and his crew actually killed this guy, the guy that proved this, because they didn't want to know the truth. And they wanted to believe that everything could be expressed in terms of rational numbers. Okay, so that's trivia set of, you know, trivia datum for you. So okay, so once we have proven that square root of 2 is not rational, we see that the rationals have holes. Okay, so the holes in the rationals are what we call the irrational numbers. Okay, and the irrational numbers, if we express them, you know, in decimal form, when you express rational numbers in decimal form, you always have this periodic expression. Okay, 0.3, 3, 3, 3. Okay, a repeating repetition. See, 7/6 is 1.1666, and it doesn't matter, you know, which period you have. For instance, if you write 23/13, you will have 1.769230, and then 669,230, and this thing is repeated up until infinity. Okay, so every time you have a fraction, you will end up with this kind of expression. Now, if you have an irrational number, such like square root of 2, you have an expression that you cannot write in periodic terms. This is 1, 4, 1, 4, 2, 1, 3, 5, 6, blah blah blah, and the numbers never repeat in a, you know, periodic sense. Okay, so in a sense, you can think about irrational numbers as those that have a decimal expansion that is not periodic. Okay, so in fact, you could, with the holes of the reals, of the rationals, you can build the real numbers. So you can think of the reals as the rational numbers plus the irrational numbers, in a sense. Okay, and the reals, we write them like this. Okay, this R. So well, because of the way we build the reals, so the reals can be thought of as, you know, every rational number you can approximate by a sequence of rational numbers. Okay, so you can get closer and closer and closer, as close as you want, to every rational number. So the real numbers, because of that, can be thought of as, you know, approximations of rational numbers, and because of that, the reals have all the properties of the rationals, which means that they are an order field as well, as we had seen before, and also they are complete. That means they don't have holes. Okay, no holes, and these holes are, you know, quotes because this is not a rigorous term. So they mean they're complete. There are no holes, and that's why, you know, when we represent them in a line, every point in a line, every point is just one number, and every magnitude that we can think of, you know, from 0 to this particular point is represented by a real number, for instance a, and only one. Okay, so there are no holes in this line, and every magnitude that you can think it can be represented by a real number. So that's why we think of the real line, because every point in the line is represented by one real number. Okay. Now from the real numbers we can get to the complex numbers. Okay, we are not going to deal with them in this course, but maybe in algebra, in algebra you will deal with them. So the complex, in the sense, they complete the real numbers in another sense. So because the equation x squared plus 1 equals 0 doesn't have a solution in the reals, but it does have a solution in the complex number. Okay, so just like the integer numbers were invented so that the equation n plus x equals 0 has a solution, and the rational numbers were invented so that the equation m over n equal 1 has a solution always, then the complex numbers can be thought of the numbers that make this equation always have a solution. Okay. So, but yeah, we won't deal with them here. And yeah, so in the notes we have some interesting facts about the reals. And so in page 15, in the notes you can read the diagonal proof. That states that there are actually infinitely many more real numbers than rational numbers. Okay, so even though rational numbers can be as close as we want them to be, and we think of them, you know, that there are many rational numbers, there are actually infinitely many more real numbers, and this is proven by this diagonal proof by a guy called Cantor, who actually went mad because of the things he discovered when he was studying the reals. Okay, so this is kind of a geek territory, but you can read about them in the notes if you want. So yeah, I think this is kind of a very brief overview of the number systems. So, but I don't want to go before talking about induction. Okay, so the induction principle. What's the induction principle? So this is a kind of a proof strategy that uses the properties of the natural numbers. Okay, so for instance, sometimes you will want to prove things that are valid for all natural numbers. So for instance, I tell you 1 plus 2 plus 3 plus blah 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 plus n, when n is a natural number, is equal to n times n plus 1 over 2. And this is true for all n in the natural numbers. Okay. And so you could say, okay, let's try it for n equals 1. So 1 is 1, it's equal to 1 times 2 over 2, 1. So this is true. For 2, we have 1 plus 2 is 3, which is equal to 2 times 3 over 2, which is 3. So this is true, and n equals 3. 1 plus 2 plus 3 is 6, and then you have 3 times 4 over 2, so 12 over 2 is 6. So this is true. But as you can see, you know, there are infinite natural numbers, and you cannot prove this statement this way. Okay, we don't know if this is true for all numbers, but if you want to prove them, prove the statement by, you know, substituting n, you will never finish. Okay, so in order to solve this, there's a proof strategy that's called the induction principle, and it has 2 steps. So the first step, let's say, is to prove these 2 things. Okay, the statement is true for n equals 1. Okay, and then 2. assuming I think there's not and then assuming the statement is true for some n, it is true for n plus 1. Okay, so if these two things are true, then the statement is true for all n. Okay, so the way to think about this is, if first we prove that the statement is true for n equals 1, okay, and so if it's true, let's call the statement Pn. Okay, we can call this Pn, which is a statement, a proposition that is a function of n. Okay, Pn is true for n equals 1. Okay, now the second thing says, well, assuming the statement is true for some n, it is true for n plus 1. Okay, if we have proven this thing as well, then, well, if it's true for n equals 1 for some n, it will be true for n plus 1. So this asserts that it is true for n equals 2. But then this statement makes sure that this is true for n equals 3. And as you can see, for every n, this thing makes sure that the next one will be true and the next one will be true, and up all the way to infinity. Okay, so instead of having to prove all of these different steps, you only need to prove these 2 times. Okay, the first one is prove it for n equal 1, and then you prove this. How do we do this? Okay, let me try with this. Well, again, for n equals 1, we have done it. 1 is equal to 1 times 2 over 2 equals to 1. So this is true. First step of the induction process is true. Okay, we have proven this. Now we have to prove the second step. Now the second step, if we assume it's true for some n, so we assume for some n that this is true. Okay, this is true for a given n. And now we have to prove that it is true for n plus 1. Okay, so is this true for 1, 2, 3 plus n plus 1? Okay, is this true? So is this going to be similar like that? We cannot write here, we cannot write the same thing substituting n plus 1, because we don't know if this is the case. But we know that up until here, this is equal to this, right? Because this is the induction assumption. Okay, so we are going to substitute this by this, because we assume this is true, and then we sum n plus 1. Now we operate with this. This is n times n plus 1 plus 2n plus 2 over 2. And then let me see. So this is, wait a minute, we can take a common factor. So we want to express this as n plus 1 times n plus 2, right? And n plus 1 times n plus 2 is just n squared plus, and then 3n plus 2, right? If you expand this, you will have this. Now if we expand this, this is n squared plus n plus 2n plus 2 over 2. So this is 3n. And this thing is the same as this thing. Okay? So this is the same as n plus 1 times n plus 2 over 2. Okay? So now we have that this expression is the same as this, which is the same as this, but writing n plus 1 instead of n, as you can see. Okay? So that means we have proven the result forever. We now know that this is true for every n. Okay? So this is the induction principle, and you need to really understand this. Okay? If you didn't understand this lecture, please watch it over and over again. Write to me, ask me, whatever. But you need to understand this, because we will use it over and over again during the course. Okay? And so I'll leave you with 2 exercises, or one exercise with 2 parts, in which you have to prove 2 statements using the induction principle. Okay, so this 1 squared plus 2 squared plus blah blah n squared is n times n plus 1 times 2n plus 1 over 6, and then 1 cubed plus 2 to the cube plus blah blah plus n cubed is n squared times n plus 1 squared over 4. Okay, and they can kind of seem difficult, but if you use the induction steps that we had just seen, okay, so first assume it is true for n equals 1, prove, test that it is true for n equals 1, so just substitute n equals 1 in the formulas and see if it's true, and then assume it's true for n and see if you can prove it for n plus 1. Okay, so that's it for this lecture.